All right. Now let's try another method. So method number 4. So we had 3 methods. We had numerically, graphically, substitution. Now number 4, we are going to cancel a common factor. So let's look at this example here. What is the limit as x approaches -3 of x squared plus x minus 6 all over x plus 3? Let me write it again. The limit as x approaches -3 of x squared plus x minus 6 all over x plus 3. That's supposed to be an x there. Alright, so we want to evaluate this limit right here. And the first thing we try is substitution. Always try substitution. But quickly we're going to see it's not going to work because we put in a -3 here. -3 plus 3 is 0. I think this is also 0. But anyways, you can't divide by 0. So it is indeterminate. So then we think, well, what's another thing we can do? Now, numerically is an option, but there's another neat technique about finding a common factor and canceling it out. So in this technique, what we're going to do is we're going to factor the numerator, and if you can factor the denominator, you also do that. But in this case, we can only factor the numerator. So we're going to have the limit as x approaches -3. All right, so what are the factors of this? We have x plus 3, x minus 2. Now the whole idea about this is, because we get 0 over 0 up here, there's a lot of times, especially with polynomials, there's a reason why it's 0 over 0. And it's because we have an x plus 3 and an x plus 3 both in the numerator and the denominator. Just this x plus 3 is one of the factors. Well, if we cancel these out, then our issue of having a 0 in the denominator goes away. And so we're going to end up with the limit as x approaches -3 of x minus 2. Now we go back to the previous step of substitution, and we get a -3 minus 2, which is a -5. And that would be our answer. Okay. Now, if we go back to this example back here, if you remember that, what is the limit as x approaches 2 of x squared minus 3x plus 2 all over x minus 2? That is the limit as x approaches 2. What is that? What is that? Minus 2, minus 1. Okay, so this was the first limit that we did numerically. And we went through the process of getting closer and closer and closer to 2. Well, if we just factor this, we would have gotten our x minus 2's out of there. And so we would have the limit as x approaches 2 of x minus 1, which is then 2 minus 1, which is 1. And so, even though we didn't have that technique when we went through that introduction, this would have been another way to figure out that this limit was equal to 1 analytically rather than numerically. All right, a couple more things. Let's go back to this one up here. One thing, or actually we can use this, one thing that's important is we are not saying that x squared minus 3x plus 2 all over x minus 2. This does not equal x minus 1. So if you remember from pre-calculus in our study of rational functions, these are not equivalent. So don't make that mistake. What we are saying is that the limit as x approaches 2 of x squared minus 3x plus 2 all over x minus 2, this equals the limit as x approaches 2 of x minus 1. Those are equal. So this is no. This is yes. Now the reason I'm kind of stressing this right now is some students get into the habit of they'll write the problem down, like they write the problem down up here, but then they start doing work without writing the limit, and that is incorrect. You will get points taken off because you can't just go from here with the limit to an equation without the limit. Those are not equal. So make sure that when you're going through this, you keep on writing the limit as x approaches whatever. Make sure you keep that. Okay. Now let's do another example, and this is more of a review from pre-calc. Let's say we have the limit as x approaches 1 of x cubed minus 1 over x minus 1. Now, you first substitute. Substitution doesn't work. So now we have to factor. But then, of course, we get to this idea of, well, how do we factor x cubed minus 1? Well, if you remember, it's a cubic. So because it's a cubic, you have factor by grouping, or we can use the rational zero test. So the whole idea of the rational zero test is that one of the zeros is going to be a combination of a sub naught over a sub n, and we're going to use, in this case, synthetic division to see if one of those works. So let's see here, we would have 1, there's the square, there's the linear, negative 1. So let's go over that again. Now because a sub naught is just a negative 1, and a sub n is just a 1, pretty much our only choices are plus or minus 1. I mean, that's it. So let's go ahead and put in a 1. So we have 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 0 plus 1 is 1. Alright, so it did work. So this x cubed minus 1 can be rewritten to be x minus 1, so remember how to interpret that, times, what is that, x squared plus x minus 1, or plus 1, sorry. Alright, so we can now write the limit as x approaches 1 of x cubed minus 1 over x minus 1 to be the limit as x approaches 1 of x minus 1 times x squared plus x plus 1 all over x minus 1. Right? These x minus 1's cancel out, and so we end up with the limit as x approaches 1 of x squared plus x plus 1. And now we can substitute, and so we end up with 1 squared plus 1 plus 1, which is 3. So that was just more a review of pre-calculus than anything new for our limit process. So here we have it. We have evaluating limits. We have numerically, graphically, substitution. Always try substitution first. And now we have cancel a common factor.